Okay, let's just quickly review the formulas we constructed for arithmetic and geometric sequences. Remember, arithmetic means each term in the sequence is found by adding some constant number, which we call d here, to each successive term. So the way we constructed those formulas is to get the nth term, we're going to take our starting term, and we have to add a certain number of those differences, and to get to our nth term, and we saw that we needed to take n minus 1 steps to go from, say, like 1 to 4 here. We had to take 3 steps to get from 1 to 4, and that's why we're using n minus 1. So it's basically our starting point, and we add n minus 1 number of steps to get to the nth term. For geometric, it's really the same thing, except instead of adding, we multiply. So to get the nth term of a geometric sequence, remember, geometric means that we're multiplying by the same ratio every time to get the next term. We take our starting term and we multiply it by r, but we do it n minus 1 times. Again, like in this case, we're trying to get the fourth term. We have to go from 1. There's 3 steps when we go from 1 to 4, so that's why we have n minus 1. So this is the two key formulas of this section. All right, example 1, we wanted to find an actual formula for the nth term of this particular arithmetic sequence. Well, let's just write down what we know. We know it's arithmetic, so we know there's going to be a common difference. First of all, we're going to find our first term, so a sub 1, we know that's going to be 3. Our common difference we can find by just subtracting any two terms, two consecutive terms. So like we could do 5 minus 3, we could do 7 minus 5, 9 minus 7. In all cases, we're going to get a common difference of positive 2. And we only have to check one pair of terms because it's given that it's arithmetic, so we know we don't have to keep checking to make sure it's arithmetic. Some problems you may need to actually check that. And that's all we really need then. So to find the nth term, again, we want to have this be a function of the first term and n. So a1 plus d times n minus 1 gets us to the nth term, and then we just plug in what we know here. 3 plus d times n minus 1. Oops, d was 2 there, sorry. 3 plus 2 times n minus 1. You can either leave it like that, it's no problem, or you could go ahead and simplify this out if you wanted to, plus 2n minus 2, and we'd have a more simplified version, which is 1 plus 2n. So now we have a formula that we could use. I think in class I'd asked you to find the 1001th term. And all you would do for that case is take n equals 1001 and pop it in there. So a sub 1001 is going to be 1 plus 2002 or 2003. Example 2. Finding a formula for the nth term of this geometric sequence. Now we know there's a common ratio, so well, again, like all these problems are going to write down what we know. We know our first term. We have the starting point here. It's going to be 3. Common ratio, we just have to divide two consecutive terms. So we'll just pick the first two here. 4.5 over 3, just to make sure we understand the notation. It's a1 over a2, and that's going to give us 1.5 is our common ratio. And again, we're using ratios here because we know it's geometric, and that's what we need. A sub n is going to be our first term times r, and then we have to multiply by r a number of times, which is going to be equal to n minus 1. So to finish this off, our formula for our nth term is going to be 3 times r, in this case, is 3 halves, 1.5 to the n minus 1. Again, you could leave it like that, or if you wanted to simplify it, you could write this as 3 times 3 to the n minus 1 over 2 to the n minus 1. And then we could just add exponents here, so it would be 3 to the n over 2 to the n minus 1. But again, you could leave it just in that simplified form there, or if you wanted to do some algebraic simplification. And see what I did here is when you multiply, you just add exponents. So 1 plus n minus 1 gives us that n right there. Example 3, here we're given an arithmetic sequence, and now we know we're given the first term and the 17th term. So, and we're trying to want to use this information to get the common difference between terms in the sequence. One way to just reason through it would be that we know, first of all, is ask ourselves how many steps are between a sub 1 and 17. So how many steps do we have to take to get from the first term to the 17th term? Well, from the first term to the second term is 1, first term to the third term is 2, first term to the fourth term is 3. So based on that pattern, we're going to have to take 16 steps to get there. And so one way to do this quickly would be just to take the difference between 106, which is a sub 17 minus -6, and that's the total difference between those terms, and that would be 112. And then knowing that we have to cover that total distance of 112 in 16 steps would give us our common difference. And if you simplify that, you can divide top and bottom by 4, and that gives you 29 fourths. Actually, I'm not sure what I was thinking there. Scratch this out. 112 divided by 16 is actually just 7. So our common difference would be 7 in this case. Now, for those of you who like to think about more of a formula-based approach here, the other way to think about this is if you just remember for an arithmetic sequence, our basic formula, the nth term is going to be the first term plus the common difference times n minus 1. Because we're taking -1 steps, we could go ahead and write this equation for 17. So instead of the nth term, we could use the 17th term. So we'll just plug in n equals 17 here, n equals 17. And then we could write this out as a1 plus d times 17 minus 1, and then use this equation to go ahead and solve for d. A17 is 106, the first term is -6, plus d times 16, and then you'll get d equals, I'm going to move the 6 over here, 106 plus 6 over 16 equals 112 over 16. That should look familiar. 7. D equals 7. So this is just an application of using this formula but solving for a different piece of information. Now this last example is we're giving a geometric sequence, and we're given the third term and the sixth term now, so now we don't even have the first term, and we need to go ahead and find T11. So I'm going to also show you two different ways to do this one. Let's go through, I'll call it the brute force way first. So T11, let's see what we would want to know if we could do it. T11 is going to be the first term times r to the n minus 1, so r to the 10th. Problem is that we don't have r and we don't have the first term. So the question is, can we use any of this information here to find those things? Well, see, if we write the expression for t to the third, we know that's going to be the first term times r squared, n minus 1, and we know that equals 12. And we know that t sub 6 is going to be the first term times r to the 5th, and that's going to equal 96. So here, we see that we have two equations with two unknowns. You have to be a little bit, there's a little bit of ingenuity here to solve that. What I'm going to do is I'm actually going to divide one equation by the other. So I'm going to take this bottom equation, r to the 5th equals 96, and I'm going to divide it by the top equation here, which is t1 r squared divided by 12. So I just, instead, a lot of times in substitution you add, but here I'm going to divide those, and then what's nice here is a lot of things cancel out. These t1s cancel out. We get r cubed equals, looks like that's going to be 8, and r is going to be 2. So we've used it to get one piece of information, then we come back and solve the equation here to get t1. So 12, I'm using the equation for T3 here. T3 equals 12 times, T3 equals 12, which equals T1 times R squared. And so T1 is going to be 12 divided by R squared, which we can see is going to be 4. So T1 is going to be 3 by plugging in, sorry, that's messy, the R equals 2 down there. So now we have the pieces of information we need. T11 is going to be that first term 3 times our R of 2 raised to the 10th power. So a different way to maybe approach this, which maybe is a little more intuitive, is just to kind of reason through what's going on here without just going straight to formulas. So try this in green here. T3, we know we're missing T4, T5, and we know that T6 we have. So if I write those values in, we have, we know this is 12, and we know this one is 96. So the first thing to ask ourselves is, we know this is geometrics. Well, if we have the third and sixth term, how many steps does it take to get from the third term to the sixth term? Well, color didn't switch. 1 step, 2 step, 3 steps. So we know that we have to multiply this term 3 times by R to get here. So we could just directly write T, sorry, use green here, T, the sixth term is going to equal the third term times R cubed. So we don't have to go through this step to find R. We have a much faster way we could find R by just reasoning through that. We know we have to move 3 times to get there, 3 steps. So here R cubed is just going to equal 96 divided by 12 equals 8, which is going to give us R equals 2 when we take the cube root. And then to find T11, we could just be resourceful, not go all the way back to T1 to find it like we did in this first step. We know that if we start with T6, how many steps is it going to take us to get to the 11th term? Well, going to the 7th term is going to be 1, 8th term is going to be 2, 9th term 3, 10th term 4, 11th term 5. So in this case, we can just subtract the 11 minus the 6 to get the number of steps it's going to be. So in this case, we could just, so if we know it's 5 steps, then we can just say that T11 is going to be T6, that's 6th term, times R multiplied 5 times to get us to where we need to go. And then we know T6 is 96, and we know R is 2, and that would be to the 5th power. And my contention is that we're going to get, that's the same answer as over there in the first half once you multiply them out. Because 3 is 96 equals 3 times 2 to the 5th, which is 32. And so when you go ahead and put that in there, you'll get the same exact answer. So 2 different ways to think about it. Again, I don't want us to be beholden to just using straight formulas all the time, and just reason through how these sequences and series work.